The cross product is the second of two different types of vector products that we have in multivariable calculus. Unlike the dot product, the result of a cross product is a vector and not a scalar. We also only define the cross product for three-dimensional vectors. There is a way to generalize this to higher dimensions, but that goes beyond this course. The book introduces the cross product on the standard unit vectors in R3. The key fact is that we use the right-hand rule on a right-handed coordinate system to derive these values. The first term of the cross product is the index finger, the second term is the middle finger, and the result is the thumb. If we swap the order, then we have to turn our hand upside down to swap the positions of our index and middle finger. When taking the cross product of two different standard unit vectors, the result will always be plus or minus the third. The results listed here are in a slightly different arrangement than the book, because I wanted to point out a pattern. All the positive results come from taking the letters in the cyclic pattern I, J, K. I cross J equals K, J cross K equals I, and K cross I equals J. All the negative results come from going in the reverse order. And so if you just remember that cyclic alphabetical order gives positive values, and reverse cyclic alphabetical order gives negative values, you'll have a much easier time remembering the results. If we use the distributive property and these formulas, we can come up with a general formula for the cross product. The calculation is just algebra and these formulas, and the book has worked it out in detail for you. We're going to jump straight to the result. Definition: the cross product U cross V of the vectors u and v in R3 is the formula u2v3 minus u3v2i minus u1v3 minus u3v1j plus u1v2 minus u2v1k. The formula looks messy, and in this form students often overlook the negative sign in front of the middle term. There are matrix formulations of this that are much easier to remember. Notice that in the bottom form, the middle row is the first vector, and the bottom row is the second vector. If you haven't worked with determinants before, it's okay to think of these as just the special notation for a specific calculation. We're going to skip ahead and talk about the physics concept of torque in order to build up further insight before talking about the geometry of the cross product. Torque can be thought of as a twisting force that is trying to cause something to rotate. Imagine that you're trying to tighten a bolt with a wrench. Where would you want to push on the wrench to make sure it's tight? If you have any experience with this, you would almost instinctively push further away from the bolt. This shows that torque depends on both the force you apply as well as where you apply it. But it also depends on the angle that you're applying the force. If you're pushing inward or outward, you're applying an unhelpful force. This is similar to pushing in a direction perpendicular to the direction of motion in a work problem. The amount of torque you get is dependent upon those three factors: the size of the force you're applying, the angle at which you're applying the force, and the location that the force is being applied. Here is the formula for torque. In this formula, the fancy T is the Greek letter tau, and that stands for the torque. R is a vector that points from the axis of rotation to where the force is being applied, and F is the applied force. Since the cross product is a vector quantity, we have put a vector symbol over tau. Be careful that when you're computing the cross product that you put the tails together. It is very common for students to just use vectors in the diagram without paying attention to this, and this can lead to getting the direction wrong. I want to take a moment to point out the differences in the book so that you know where they are. The book uses torque is equal to F cross R instead of R cross F. In the book's diagram, the vector R is backwards from the convention, pointing from the place the force is being applied back to the axis of rotation. It turns out that these two differences cancel each other out, and the curious student may want to think about how they might verify that for themselves. The third difference is that the angle theta is not the conventional angle between vectors, which is the angle formed when the tails are put together. For various formulas involving the sign of this angle, it turns out it doesn't matter and you'll get the same result by following the book's presentation. So there's nothing mathematically wrong with the book, it's just different from the physics conventions. Similar to the work problems with dot products, we're only going to look at the most basic applications, so at some level it doesn't even matter which way you do it. If you do look up more information and go deeper into the topic, you're likely to see other formulas for torque. Here are just some possibilities. The first equation is the standard version for physics using vectors. The second equation involves a concept known as the lever arm or the moment arm. We're not going to define it here because it's not relevant to this class, but you should be careful because this value may not be what you might intuitively guess it is. So be extra careful with that one. The third one is actually related to something we're going to see in the next video, which is why I'm including it here. For this class, we care about the vector form the most because we're getting practice with vector calculations. An interesting conceptual piece of this is that the direction of torque corresponds to tightening or loosening screws. Most of the screws you interact with are right-handed screws. If you're familiar with righty-tighty and lefty-loosey, that's a right-handed rule. If you're tightening a screw, the torque points inward, and if you're loosening the screw, the torque points outward. You will sometimes see these symbols for vectors pointing directly in or directly out of the page. You should think of the cross as the fletching of an arrow, which are the feathers or plastic parts on the tail end. And this dot should be thought of as the tip of the arrow pointing out at you. It's important to know that there are left-handed screws and threads that do the opposite of this, so it isn't some rule that all threads have to behave this way. But the overwhelming majority of the screws that you will run into are designed like this. In the next video, we're going to take a look at the geometry of the cross product.